Very good morning to my dear students. I, Harita Malani, working as an assistant professor in Electronics and Communication Department of MLP Textile and Engineering College, Bhilwara. Today I am going to discuss in continuation with my previous topic, cyclic codes of subject information theory and coding. So next I will discuss generator and parity check matrices of cyclic code. One method we have discussed in our previous slides. Now I will discuss the second method, how it is easily formed. So the steps are dividing x n minus k minus I by the generator polynomial g of x. So this is to be find out ai x gx plus bi of x, where b is a remainder polynomial. So remainder polynomial is written like this plus this and multiply of g of x, they are the code polynomials. So I will get the code polynomial by multiplying that. So now arranging these k code polynomials as row of k cross n matrix. So this G is defined, which is a generator matrix of C in systematic form. So directly here I am getting C code generator matrix in systematic form. In previous method, first I will get in systematic form and then I will get systematic form. The corresponding parity check matrix, we all know, we have discussed in LBC codes. So how to find that? So next, again let G of x dividing x cube, x4, x5, x6 by G of x. We have x cube is G of x plus 1 by 1 plus x to the power 4, x gx. Rearranging the equations above, we obtain the following code polynomials. By rearranging this, I will get all my code polynomials. This is one of the example. Continuation with that, taking this 4 code polynomial as rows of a 4 cross 7 matrix, we obtain the following generator matrix in systematic form. See here, what I have did, I have find out these bits. These bits are providing me V0, V1, V2, V3 code polynomial. From this, I can write my generator polynomial. The generator matrix is this from the previous example. Now encoding and decoding of cyclic codes is must. Here we have to draw some block diagrams. How I will draw the block diagrams? I have to first denote the data polynomial, message polynomial, then I have to follow the generator polynomial, then I have to put a modulo 2 operation. So encoding consists of 3 steps. First, multiply the message polynomial u of x by x to the power n minus k. Same steps we studied earlier is to be implemented by using block diagrams. So dividing this by g of x to get the remainder polynomial from the code word. These are the steps which we discussed. Now all these 3 steps can be accomplished with a division circuit, which is a linear n minus k shift register with feedback connections based on the generator polynomial. So you will see the encoder designed for cyclic code. So this is the design of encoder. So what we are doing over here, a very simple block diagram for any order n comma k you can design. Clear? So how I will start? This is my code word. I will give the code word. It will go to this modulo 2 operator. Modulo 2 operator, one gate is there. Okay, when this gate is on, this data will be passed to first polynomial B0. B0 G1. B0 G1. B0 is the first data polynomial. B1 B2 Bn minus k minus 1. So if I am having, these are my bits. Message bits are going through this. Message bits are going through this. So B0 polynomial multiplied by G1. G0 and Gn minus k will be always 1. These are always closed circuit. G0 and the last polynomial. In between it could be on and off, 1 or 0. Open loop or closed loop. So B0 multiplied by G1 will give you B0 mod G1. Clear? This B01 plus G1 of x. Then B1, this is multiplied, this modulo 2 operation act as input to this B1. Then this B1 is modulo 2 added by G2. So in continuation with this, last bit will be B of n minus k minus 1. And I will get the output from here. I will shift this switch. This is a switch to get parity check digits. So what I am designing an encoder. That means encoder means designing of parity check bits. That means for n comma k, k is my 4, n is 7. So I will get 3-bit data over here. This 3-bit data will be added, multiplied by your input data bits to get the final code word. So here I will get parity check bits B0, B1 and B2 for 7,4 CC codes. So all the steps are mentioned. You can study this step from this. I have shared all the data with you, so you can study from that. Next, this is the example. Consider 7,4 cyclic code generated by g of x. Given the encoding circuit based on g of x is shown in figure 5.2. You can see the figure. This is my figure. How many shift registers are used? Only 3 shift registers are used. 1, 2 and 3. Clear? And first G0 polynomial and Gn minus k polynomial is always 1. In between it depends on the generated polynomial equation. Here Gx is 1 plus x plus x2. We know this is 7,4 code. So I have 7,4 n minus k is 3 bit parity digits. So B0, B1 and B2. Clear? So here the encoding circuit based on g of x is shown. Message is this. To be encoded as a message, digits are shifted into the register. The content in the registers are as follows. Initial state we always consider as 0, 0, 0. So first data bit is my 1. This 1 will be shifted. So 1 is in B0. Clear? First shift register, initial state, I will multiply this. Here I am having 1. At first shift 1, 1. This 1 will be shifted over here. Here it's 0. So what I will get? I will get first shift 1, 1, 0. After that again 1 is going, after 4 shift the content of the register. After shifting this data I will get 1, 0, 0. This we will see. This is a diagram and all the description is given over here. How we are getting the output. So you can draw this diagram. One by one you shift the data, perform modulo 2 operation, you will get the output. So this is encoding circuit for n, k cyclic code based on priority polynomial. The feedback connections are based on the coefficient of parity polynomial h of x. The encoding operation can be described in the following steps. Step 1, initially gate 1 is turned on and gate 2 is turned off. The k information digits u of x is equal to this are shifted into the register. So first gate is opened, all the data bits will be loaded into the shift registers. As soon as the k information digits have entered, the shift register gate 1 is turned off and gate 2 is turned on. The first parity check digit is this, is performed and appears at point P. The first parity check digit is shifted into the channel and is also shifted into the register. Second parity check bits, same steps are repeated till all the data bits are fed into the register and we will get all the shift registers with parity check bits. So this is one more example over here. 7,4 cyclic code generated by g of x is h of x is what we are doing. We have to multiply the first data bit into x of n minus k divided by g of x to get the remainder polynomial. So these steps are simplified. Suppose that the message to be encoded is this 1011. So then V3 is 1011. Now this is my designing 4 shift registers. This is my initial register. This and this are the 3 registers. As generator polynomial is having 4 bits. Encoding of cyclic code, the first check digits are this V2, V1 and V0 and you will get the output as 0, 0, 1. V0, V1, V2. So this we will put. So next is my syndrome computation and error detection. So syndrome calculation is S is equal to RH transpose. We all know this thing. So if syndrome is 0, that means received code vector is same as the transmitted one. And if syndrome is not 0, then there is some error. So error vector we have to find. Rx is the polynomial, received vector polynomial. So decoder can be designed accordingly. This is my syndrome circuit. Syndrome calculation means designing of decoder where error exists and in which bit error exists. So syndrome calculation is the decoder calculation. So these are the simplification of syndrome computation and error detection. So I think you will understand this concept of syndrome decoding and error detection process. So thank you students.